Hey everybody, Trey here. Welcome back to another video. We've had a very active stretch of severe weather, especially across the southeast over the last few days, centered on Friday, March 24th, when we had multiple strong to violent tornadoes occur across parts of Mississippi into northern Alabama, most notably an EF4 tornado that went through the town of Rolling Fork, Mississippi, killing about 24 people there, unfortunately. Very upper echelon tornadoes from a very potent setup. As always, after these events that unfortunately take the lives of a lot of people, the best thing we can do is to study these events and figure out why these storms happen as they did. And that's what we're going to do in this video today. We're going to take a look at the environment behind the strong and violent tornadoes that occurred across Mississippi on March 24th. Take a look into the meteorology, the background pattern, as well as some smaller scale features that may have impacted tornado genesis in these supercells. So, without further ado, let's go ahead and get started. Just to give some context here, these are the preliminary tornado tracks from damage surveys done by NWS Jackson and Memphis on the three major tornadoes that went across Mississippi back on Friday, March 24th. This one farthest to the southwest is the Rolling Fork tornado. Rolling Fork is right in there. You see a couple of areas of those red triangles. Those indicate EF4 damage indicators. This was an EF4, at least preliminarily rated an EF4 with winds up to 170 miles an hour. This was in progress for about 60 miles, tearing through towns like Rolling Fork, Midnight, and Silver City, Mississippi. The storm then cycled and produced another strong tornado that crossed Interstate 55 near the town of Winona. This one was rated EF3 and was in progress for about 29 miles. Another tornado here in northeast Mississippi. This one went through the town of Amory. This has been rated preliminarily an EF3 as well. Winds of about 155 miles per hour here. This one had some pretty impressive radar data, including debris signature. A pretty impressive debris signature with it, and we'll take a look at that in just a bit, but very impressive. This was not a widespread tornado outbreak per se, but this one storm produced a number of strong to violent tornadoes that tore a path across Mississippi back on Friday. This was a very well forecast event. This was the SPC convective outlook for day 6. So this was issued on March 19th. Again, our event was on March 24th, indicating a threat for severe weather anywhere from East Texas up into the Mississippi, Alabama, Tennessee region there, and the forecast would only further refine as we went into the coming days. Day 3, with our probabilistic outlook, our first probabilistic outlook had an enhanced risk across that Mississippi River Delta region from eastern Louisiana into much of western Mississippi with a 30-hatch significant severe area. And by day 2, we had a moderate risk out within that region, 15-hatch for tornadoes, strong damaging winds as well. And then by day 1, that would be maintained, that moderate risk, with a 15-hatch for tornadoes and a damaging wind threat throughout the entire day, centered right on that Mississippi River vicinity there of far southeast Arkansas, northeast Louisiana, into northwest and western Mississippi. All right, let's dive into the meteorology behind this event. I'm going to put a link to my forecast discussion video from the morning of Friday, March 24th in the description below, because what we talked about in that video really played out as expected. We'll start here with the 500 millibar map. This is going to be at 12Z, so 7 a.m. Central Daylight Time on Friday. Right away, you see a very broad trough across the desert southwest into western Mexico, somewhat neutrally to maybe slightly positively tilted. And as we talked about in that video, the progression of this trough was fairly classic. The ejection of the trough was fairly close, fairly similar to a lot of previous tornado outbreaks. And in that forecast discussion video, we actually compared it to the April 27th, 2011 super outbreak trough ejection. This is some archived 500 millibar data from April 27th, 2011. Notice how the trough centered up in the Great Lakes region with a somewhat positively tilted axis here on the morning of April 27th. Watch what happens as we go through the day on April 27th. That shortwave trough takes on a much more negative tilt here with a strengthening jet streak rounding the base of that trough, and your main area of interest with that particular event was just on the southern or southeast side of that jet streak. Very similar progression here with our 500 millibar trough. Let me back it up a little bit and go through it with some speed here. You see it takes on that much more negative tilt by early evening, and the winds in the rounding the base of that trough strengthen a little bit. You can see that jet streak there, upwards of 90 to even 100 knots or so there within that flow. And your main area of interest was just on the southern or southeast side of that jet streak there, right where that moderate risk region was, generally in your right exit region. Now, some of you may have heard before, if you studied upper level troughs, that the left exit region is usually the favored quadrant of a jet streak for significant severe weather and tornado outbreaks. But this is a perfect example of why you should never overlook the right exit region. And the reason for this, if we take a look at a jet streak here, let's take a look at our jet streak. So if we were to break this up, say that's our axis, and we were to break this up in two quadrants, the science behind this says that the right or the left exit region is where your vorticity is highest, that spin in the atmosphere is highest, and that's where your divergence aloft is going to be highest, leading to upward motion favored in that left exit region. Your right exit region is slightly more favorable for convergence aloft, and as a result, that promotes somewhat of slight sinking motion in that right exit region. But we're still in the exit region of the trough. We're still in that favorable sector for forcing in the trough, and even the forcing in this right exit region, as we see here, may even be a little bit weaker than it is in the left exit region. We saw the storm mode here in the left exit region, closer to that surface low, become much more messy with time, whereas down here, a little bit farther removed from the actual jet streak here, just on the southern side of that, a little bit weaker forcing, a little bit more tendency for storms to become discrete, and so you can never overlook the right exit region of an upper level trough, as evidenced here with this setup. If we were to draw our axis here and we were to split this into axes, our right exit region was where our major tornado activity happened with this particular setup, even though that may not be your quote-unquote favored quadrant for significant severe weather. This was a textbook example of why you should never overlook that right exit region, especially if you have any weaker forcing mechanisms within the open warm sector in that right exit region, such as prefrontal confluence bands or prefrontal troughs. We're going to talk about how those came into play here with this particular event in just a second. So once again, we had our trough ejecting into the southern plains and southeast by late afternoon into the evening, taking on a much more negative tilt, and as a result, we got quite a bit more of a robust low-level response, which we'll take a look at in just a second. Let's go down to 700 millibars, take a look at any short waves embedded within the flow. And you'll see a bunch of different kinks here within the broader trough here. You see one, this is at 21Z, so 4 p.m. Central Daylight Time, one over here over Arkansas, one back here in North Texas. This one over Arkansas may have been convectively induced. We had quite a bit of convection ongoing at this point across Arkansas ahead of the surface low that was developing and moving off to the northeast. So that may be convectively enhanced. We do have a couple here rotating through the main trough. Hard to say if any of these had a legitimate impact. There is a shortwave that does appear to be right in the eastern Arkansas to northwest Mississippi corridor right there. Again, not sure if that is convectively enhanced or not, but that could have played somewhat of a role in initiating storms down there in Louisiana. The main initiating mechanism, though, was a prefrontal confluence band, which we'll take a look at here in just a second. But down to 850 millibars, and as that trough moved through, took on a more negative tilt, strengthened just a little bit, that's when we had our more robust low-level response. You see through much of the day, we have a broad, just troughiness here across the central portion of the country, just troughiness here at 850 millibars, with a decently strong low-level jet across the region of about 30 to 35 knots through much of the day. But as we went through into the evening hours, the late afternoon into the evening, we started to see that trough again take on a much more negative tilt, strengthen just a little bit, and that initiated a stronger low-level mass response. And as a result, our low-level jet strengthened during the late afternoon into the evening hours. You see here, we get some closed contours up here across Missouri, indicating a strengthening low-level cyclone. And you'll notice here in these wind barbs, we jump from at about 23Z, about 30 to 35 knots here across Mississippi into Alabama of low-level jet. In just a couple of hours, we've strengthened to 55 to 60 knots here across this region. We know what that does. That, number one, helps to really start pumping that moisture into the region, and that was a necessary factor across this region because we had some vertical mixing going on. We're going to talk about that in a little bit here. But this initiated strong low-level warm moist advection, and it also helped to really enlarge low-level photographs, which you'll see as we go through a series of soundings here in just a bit. So the low-level mass response really ramped up after dark. right just before sunset and after sunset, we really saw that low-level jet spike, and as a result, we had a very favorable-looking warm sector primed for long-track tornadic supercells. Same thing you'll see here down at the surface. We have just broad surface low features down here across Texas. Maybe one center down here in far south Texas, one up here just south of the Red River, but very broad, somewhat nebulous low-level cyclogenesis here. But that was not the case as we went into the evening hours. Once again, that upper level, what happens in the upper levels is tied to what happens in the low level. So as that upper level trough strengthened and took on a little bit more of a negative tilt, we had a much stronger surface cyclogenesis response. You'll see a tightening of those surface pressure contours, those isobars, into Arkansas. This is at 23Z, 6 p.m. Central Daylight Time. Very strong surface low developing at this point right across Arkansas. Fairly progressive off to the east, a lot more forcing up here near the surface low track helped to organize those storms with northern extent into more of a messy or linear mode, and therefore the overall long track tornado threat was not quite as strong up here into Arkansas and western Tennessee. But down here to the south, we had a wide open warm sector just to the south of that surface low. Here is our surface station plot data, and right off the bat you'll see we have a frontal zone that's stretching from the Midwest, northeast to southwest, down through Arkansas, into southeast Oklahoma, into northern and central Texas. This was a frontal zone that was a major feature in the previous day's severe weather event across Oklahoma and Texas. We had a number of severe storms here, mostly elevated, mostly just produced some large hail as the boundary was sagging to the southeast throughout the day on Thursday. But because, as we saw, the trough was hanging back a little bit farther into the southwest, we just had broad southwesterly flow across the region and a lack of robust surface response. This cold front, or this somewhat stationary front, you could call it, was not moving very fast at all to the east or southeast. That allowed a very broad warm sector to develop from all the way from central Texas through the southeast states, as we talked about in our morning forecast discussion on Friday. All these green values, the dew points, in the 60s here, all the way into Alabama and likely off the map into Georgia and Florida. So we had a very broad warm sector, creating a lot of real estate for any type of severe weather event to take place within. And so anytime you have this broad warm sector with somewhat subtle forcing, as we just talked about a little bit ago, that is a setup to really keep an eye on. Now we have dew points, as you see, as we said, in the 60s, even 70s down here into East Texas and along the coastal regions, but very broad sector of mid to upper 60s dew points up through Arkansas into Tennessee. A very broad warm sector, no doubt. Now, I want to interject here and just show the satellite view, and this was what it looked like on the morning, on Friday morning. And as a storm chaser, when you wake up to this kind of satellite imagery and this kind of sky in a southeast setup, you get excited because oftentimes in these southeast setups you'll have a lot of forcing and therefore a lot of clouds and showers in the open warm sector, and we know that that can prohibit instability from actually building, and that can keep lapse rates at bay, and you may not get super robust updrafts within a given environment. Oftentimes that's the case in the southeast, but when you see a sky like this, that's not going to be the case. You're going to have a lot of surface heating, allowing those temperatures to warm, those lapse rates to steepen throughout the lower atmosphere, and as a result you can really get instability to build to act on a typically very strongly sheared environment. But this was a double-edged sword, because although you have that instability being allowed to build throughout the day because of this ample surface heating, that can also initiate vertical mixing. We've talked about vertical mixing before. That's when you have strong surface heating from the sun that can, and we know that warm air likes to rise. So as that low-level air near the surface warms up, that can rise into the atmosphere. But it can also initiate mixing, meaning that air from aloft gets mixed down to the surface. And if you have drier air situated aloft here, that can allow dew points and low-level moisture to decrease throughout the day, which is obviously not favorable for severe weather. We'll do some more in-depth sounding analysis in just a bit, but this was the 12Z sounding at Lake Charles, Louisiana, so southwest Louisiana. And you'll see a bunch of dry air aloft here, just above a very shallow very shallow moist layer near the surface. Lots of dry air working in, a pocket of drier air evident at New Orleans as well. This was the Slidell sounding, just a lot of dry air aloft here. Unclear where this dry air came from, but it was working its way in, and given the ample surface heating that was going on here when the sun came up and through the morning and afternoon hours, This allowed dew points to drop a little bit throughout, especially Mississippi. Keep your eye on Mississippi here, dew points in the mid to upper 60s. But watch as we go through the day. You'll see those dew points drop quite a bit as we go into the afternoon hours. For example, here at Greenwood, Mississippi, we start off the day 72 over 65. Dew point drops pretty significantly to 60 there, and with temperatures rising into the low 80s. So temperature dew point spreads were quite high across the northern half of Mississippi as a result of vertical mixing. So this was a concern going through the afternoon hours, but it was expected as that surface low tightened up throughout the region, as we looked at in our mesoanalysis data, as that surface low and low-level response started to become a lot more robust as that low-level cyclone tightened. That warm and moist advection was expected to overcome that mixing quite a bit as we went into the afternoon and evening hours, and that's exactly what happened. You'll see the temperatures drop, of course, as we start to lose the daytime heating. Those dew points, though, went up quite a bit. You'll see Greenwood, Mississippi jump up to 66, 68 degrees there. I believe that is 68 right there. So the dew points definitely rebounded quite a bit. Jackson, Mississippi, you can see that as well. Here is Jackson. You'll see that dew point goes in the span of just a few hours. This is at 22Z, so 5 p.m. Central Daylight Time, 82 over 63 at Jackson. And then over the next couple hours, we really see that moisture advection kick in, and those temperatures cool a little bit, 74 over 69 by 1Z there at Jackson, Mississippi. Therefore, that mixing, that decrease that low-level moisture, was overcome pretty nicely from that strong low-level warm moist advection there at the surface. And you'll see here with our 0Z Jackson sounding, we do have a little bit of that inverted V profile there, indicative of some mixing that had gone on during the afternoon, but still the moisture, the surface dew point was increasing, and we had seen a very solid moistening of the entire profile as we went through the late afternoon and evening hours with this particular setup. Another thing I wanted to point out as far as the surface data goes has to do with this cluster or line of storms that extends back into Arkansas here. If you look really closely, it's a little bit hard to tell from this zoomed out view, but you'll see that those storms appear to, instead of move, they appear to propagate. And what I mean by that is that instead of a single storm that just moves and translates across the landscape, these storms appear to be regenerating new updrafts on the leading edge, and therefore they're more propagating rather than moving. That tells me that these were fueled by significant outflow. These storms were spitting out outflow, and as that outflow was surging a little bit farther southward. And that's exactly what we got. We had our remnant frontal zone draped across here, but the outflow was reinforcing this frontal zone to the south across central and eastern Arkansas. I thought that could be a potential corridor for enhancement in tornado potential throughout the remainder of the afternoon. You'll see here the wind shift. See a pretty clear wind shift right here across central Arkansas. Here's Little Rock right there. And you'll see the winds are out of the east at that particular station, just to the south of there, winds out of the due south. So there was definitely some sort of outflow in this region right here from those storms, and that would cease throughout the late morning hours, and that boundary would just somewhat sit there throughout the day. You'll see by 22Z still have that little bit of wind shift in there, and I thought that would be maybe a favored corridor for those storms that fired in western Arkansas to potentially use to enhance the tornado potential given stronger low-level shear along the boundary. That did not end up happening. We did have a number of storms here across central Arkansas, but given the overall closer proximity to the stronger forcing aloft and the overall quick progression of this surface low, you'll see here early on by 12Z or 13Z, you see a little bit of a wave potentially along the front here in north central Texas. We get more robust surface low development later on here. This is at 20Z. Right there is your surface low at the Oklahoma, Texas, Arkansas triple point there, and then it moves off to the east very quickly, and as a result, the storms were much more organized in a more messy fashion or linear fashion up here. A few tornado warnings up in Arkansas, but no confirmed tornadoes that I know of up here, but those tornado warnings perhaps were fueled by the leftover outflow reinforced portion of the front here in central and eastern Arkansas that you can clearly see on surface data. By 22Z here, you can see that cold front had not moved a whole lot, moving into southwest Arkansas, far northwest Louisiana, and east Texas. So at the start of the day was somewhere in this vicinity here, had not moved a whole lot in the late morning to mid-afternoon hours, and as a result, that warm sector remained fairly broad down here to the south, leaving again a lot of real estate for supercells to take advantage of here across Louisiana and Mississippi as we went into the early evening hours. All right, let's take a look at some observed soundings from across the region. We'll do a little bit more of an in-depth look at a progression of RAP model proximity soundings in close range to the tornadic supercell in just a bit. But for now, we'll look at the observed soundings to get a better picture of the environment across the region. This was the Thursday evening sounding from Dallas-Fort Worth, and you can see already a very favorable profile upstream of our moderate risk region for Friday. Take a look at this moist layer. This moist layer is just crazy. Goes up almost to 700 millibars here. That is pretty astounding. Very high quality moisture across the region. We are seeing a little bit of that mixing going on. 81/63 there at Dallas-Fort Worth. That little bit of inverted V profile at the base of the skew T, but still a very deep moist layer, very high quality moisture beneath somewhat of an elevated mixed layer. We talk about the elevated mixed layer pretty much every video on this channel. The EML is that layer of warm, dry, well-mixed air that emanates at and just above the surface in the desert southwest or western Mexico and gets transported into our target area, whether it's the southern plains or southeast, atop the moist layer. And that helps instability to build in a given environment. And we have that in spades here. Very deep moist layer beneath somewhat of an elevated mixed layer. This is a classic loaded gun sounding upstream, what was expected to advect into the region for Friday. In addition, a very favorable looking wind profile for supercell, strong deep layer shear, effective shear of about 50 knots, with strong low-level shear and curvature in that hodograph as well. So this was a very favorable look already upstream of our target area for Friday. And that didn't really change too much going into the morning hours of Friday. This is the 12Z Shreveport sounding. So just off to the east a little bit in the warm sector, still holding on to a very deep moist layer up to about 800 millibars or so beneath somewhat of a capping inversion. A little bit of dry air there with strong deep layer shear, a little bit of a wonky profile that would get worked out as the day went on. But farther south, that's where we started to see that dry air. We talked about this a few minutes ago, but that dry air, that moist layer, first of all, was much more shallow, did not quite extend nearly as high up into the atmosphere as areas farther west there at Dallas the night before and Shreveport in the morning of Friday. But very dry air just above that moist layer that was working its way in. Same thing at Slidell near New Orleans, 12Z sounding here at Slidell, very shallow moist layer, ample dry air aloft. So this was of some concern, as we had said, that this might induce vertical mixing given that strong surface heating, and we may see moisture crater a little bit as we went into the afternoon hours. But as we said, that was not too much of an issue going into the afternoon and evening, given strong low-level warm advection. Here's the 12Z Jackson sounding as well. We showed that earlier. Again, decent moist layer up to about 850 millibars, but that layer of dry air aloft was a little bit pesky. Now, as we went into the day, this is 18Z at Shreveport, and you can see there the moist layer had deepened somewhat as well. Still a little bit of that elevated mixed layer aloft. And so areas farther to the west, a little bit farther removed from that drier air, had a little bit better thermodynamic profiles, a little bit better skew Ts throughout the day, whereas we had to work on those areas in areas farther to the east where that dry air was in place. Here is Lake Charles. We go from 12Z to 18Z, and as you notice here, not too much of an issue getting that dry air out of there. Very deep moist layer once again. We had kind of rectified that issue. Deep moist layer now up to about 700 millibars or so. Little pocket of dry air still, but very strong thermodynamics here. Mixed layer CAPE above 1,000 joules per kilogram already there at 18Z or 1 p.m. Central Daylight Time, with some decent looking low-level thermodynamics as well. We go to Slidell, same thing there. Decent improvement from the morning sounding. Still some dry air aloft above about 850 to 700 millibars to work with, but we had deepened that moist layer once again. And so strong low-level warm moist advection was taking place and helping to eliminate the really bad dryness in some of these skew Ts early on. And you can really see the progression at Jackson. So this is 12Z at Jackson. We go to 18Z. Moist layer had deepened. A little bit of mixing, as we said, 80/64 now. So that little bit of inverted V profile worked its way in with some of that mixing taking place. But that moist layer overall had deepened just a little bit. Still had some of that capping in place at 18Z. Here is 21Z. We had even further deepened that moist layer. Now it's up above 700 millibars. That is pretty incredible to see that deep, deep moist layer extend above 700 millibars, or about 3 kilometers into the atmosphere. That is a super, super deep moist layer. Again, the mixing was pretty rampant across the region, 83 over 63. Very high temperature dew point spreads across the region, especially for southeast standards. But the overall moist layer was very, very deep. You'd had a little bit of that, a little erosion of that elevated mixed layer, and by 0Z, that elevated mixed layer, that capping inversion head, we'd gotten rid of that pretty nicely. Still some remnants right there, but overall that capping inversion was gone by 0Z. And that's when we had a real uptick in the intensity of the storms across the region. Once again, we said those temperatures dropping off just a little bit as we went towards sunset, and the moisture was increasing. We went from at 21Z, 63 degree dew point there, up to 65 at 0Z, and we'd continue to see that moistening thanks to strong low-level warm moist advection across the region. Same thing at Slidell here. You see that as we go into the evening, 0Z sounding, very deep moist layer once again. So that, thanks to that surface low and low-level cyclone deepening very rapidly as we went into the late afternoon and evening hours, we had that very strong warm moist advection take place to really deepen that moist layer and really erode that capping inversion at a pretty decent clip by evening. Wind profiles as well. Back to the west here at Slidell, fairly good looking wind profile, 50 knots of bulk shear. So strong deep layer shear for supercells, and some strong curvature there, strong veering of those low level winds with height. Same thing at Jackson, and we would continue that after dark. We'll take a look again at some more soundings past 0Z as we do our RAP proximity sounding analysis in just a bit, in close proximity to the ongoing tornadic supercell. But overall, very strong looking profile still here at 0Z, about 350 meters squared per second squared of effective storm relative helicity at Jackson, and very strong streamwise vorticity. We've talked about this many times before. Streamwise vorticity is when we have our storm relative wind vector drawn from our storm motion vector to our point of interest on the hodograph, and we have our horizontal vorticity vector, which is always perpendicular and to the left of the hodograph. When these two vectors are parallel, that's when you have streamwise vorticity. You can think of it as an NFL quarterback throwing that perfect spiral with the football. That's what the storm is ingesting. If you have crosswise vorticity, when these two vectors are more perpendicular to each other, the atmosphere has to fix that a little bit, and it's much less favorable for tornadogenesis in supercells than if it's ingesting streamwise vorticity. It's already got that perfect spiral ingested into the updraft, makes it much easier for these storms to produce tornadoes than if you had more crosswise vorticity. So very strong streamwise vorticity here at the observed Jackson sounding at 0Z. Fairly decent thermodynamics as well, 1,000 joules per kilogram of CAPE, mixed layer CAPE, strong storm relative helicity in the low levels that was only growing with time as we went past sunset, and the environment, this was setting the stage for a very potent environment for long track tornadic supercells. So as we turn our attention to the radar here, we'll start at about 7 a.m. Central Daylight Time on Friday morning. A couple of areas of storms ongoing at this time. We had that band of storms we were talking about that was producing outflow from central Arkansas into far northwest Tennessee, western Kentucky. Then we had a secondary batch of storms out to the west, western Arkansas into Oklahoma and North Texas. That was basically the remnants of the Thursday activity. We had storms continue into Thursday night and Friday morning, and that was what was ongoing as the sun rose on Friday morning. We go through with time here, and you'll see that the warm sector stays pretty free and clear of convection through much of the morning. As we said, some of that remnant capping and the overall forcing being just a little bit displaced off to the north helped keep that warm sector free and clear of storms throughout much of the morning into the early afternoon hours. We did start to see some activity initially back on the cold front across Texas, northeast Texas into east Texas. That fine line right there is your cold front, not moving off to the east very quickly at all, as we discussed. So that, again, left a lot of real estate for these storms to use in that very broad warm sector. So storms continued to fire along the cold front, and we started to see some showery activity here across East Texas into Louisiana along these confluence bands. These would come into play very significantly in this particular event. And you can see fairly discrete development along those confluence bands, a separate area as well out to the east in far southwest Mississippi, southeast Louisiana, that would initiate a supercell there as well. So we continue to move forward. And those storms across Arkansas, given very strong forcing here, as we discussed, these storms were very quick to transition to a more linear mode. A couple of tornado warnings up in here, but the surface low was progressing east very rapidly, and therefore the forcing was much stronger, closer to the jet streak associated with the shortwave trough, and therefore much more linear mode down up here in Arkansas, in the northern portion of the risk area. But down here along these confluence bands, much more scattered convection. And this confluence band here across south central Louisiana is what we were watching closely to see any discrete supercell development later on. These storms in southwest Mississippi continued. This one would become a tornado-warned supercell that moved very close to Jackson, Mississippi. Although, as we talked about, those spreads, those temperature dew point spreads, were quite high as this storm moved off toward the northeast. We'll go back to our surface data here. You'll see that those spreads, even though storms were ongoing down here, they were moving into this environment up in here. 81 over 60 at this particular station, 82 over 63 at Jackson, 82 over 62 at Greenwood, Mississippi. So the mixing had taken its toll out here across Mississippi. So even though we were seeing discrete storm development down in southwest Mississippi, we're not too confident that it was super conducive for tornadic activity given such high spreads. And perhaps an increased potential for this storm to produce outflow. It did try to wrap up a little bit as it moved toward Jackson, had a tornado warning on it and a decent-looking couplet at times, although I do not believe it produced a tornado during its life cycle. We'll take a look at the satellite now, and once again, a very favorable-looking sky if you're a storm chaser in this area to wake up to for a southeast event. But as we said, that mixing took its toll here in Mississippi. Full-on sunshine through much of the morning into the afternoon allowed that dry air to get mixed down to the surface. Back out here to the west, a little bit cloudier, so kept temperature dew point spreads at bay, plus the moisture, that strong low-level moist advection was working its way in from the west or southwest, and so the moistening was occurring back out to the west. And you'll see these little bands of clouds as these storms start to get going across East Texas. You'll see these little bands out here. They're a little bit difficult to tell, but you can see these little updrafts right along this band here from southwest Louisiana northward, a couple out in here as well. These are called confluence bands, and confluence bands are basically just when you have slightly convergent or confluent flow that creates some sort of boundary and a more mesoscale area of lift. Given that the forcing is very weak along these, convergence along these bands is quite weak, you can actually get very discrete, isolated, more scattered development along these bands, and that's exactly what tends to produce these discrete supercells in open warm sector environments. These very subtle confluence bands, and you can see the updrafts continue to mature along them, right along this band here. And again, we were watching this one closely across central Louisiana for discrete supercell development, moving into a very favorable environment that we took a look at just earlier across the area. Some low-level stability across Mississippi and areas out to the east, but that would wear off as that low-level warm moist advection continued as that surface low deepened throughout the late afternoon and evening, and those storms would they would putz along a little bit. Here's your Jackson storm out here that was moved just east of Jackson that was tornado warned. But right along here were these storms that would eventually move into far northeast Louisiana and western Mississippi that would be our main show. All right, let's zoom in a little bit on our Louisiana-Mississippi sector here. So as we go through in this radar loop, you'll see what happens. Lots of showery activity here across southwest Mississippi, southeast Louisiana, associated with the eventual Jackson supercell. But you see this fine line on radar. This is our confluence band right here. And you'll often see these take shape in these open warm sector setups, these just fine lines of light, showery activity where updrafts are forming along it. And again, the convergence or confluence along these bands is fairly weak, so you often will get discrete development out of these bands. And you can see down here across central Louisiana, this was our eventual area of updrafts that would spawn our Rolling Fork supercell. You can see, though, that they took a while to become robust enough to produce tornadic activity. They cross the river, and then eventually they start producing tornadoes just as they cross the Mississippi River into far western Mississippi. Now, why is that the case? Well, in these strongly sheared environments, in these high wind shear environments, it often takes some degree of clustering or slight upscale growth to allow these updrafts to resist the wind shear and not just get toppled over and shredded by the strong wind shear in play. Think of the analogy where let's say we have a single tree standing in just a flat landscape, a single tree, in the eye wall of a hurricane. So you're getting battered by, say, a strong hurricane, 140 mile an hour winds per se. That tree is going to probably fall over. It's just a single tree, nothing to shield it from the wind outside. It's just going to fall over. But what if we have a grove of trees or a forest of trees in that same environment? Well, you're probably going to see some of those topple over and be toppled by the wind, but you're going to see a lot of those still standing because those trees work together as they're clustered together to shield themselves from the wind. Same thing with these highly sheared environments. If you just have a single small updraft going up in a very highly sheared environment, that shear is going to rip it apart. It's going to shred it, it's going to tilt it quite a bit, and you're eventually going to see that updraft evaporate. But if you have a lot of updrafts in close proximity to each other, not so much that you have an instant squall line or instant upscale growth into a more messy storm mode, but if you have a few of these updrafts clustering together, that can allow these updrafts, at least some of these updrafts, to resist that wind shear, not get torn apart immediately. And as a result, that is how these storms can sustain in these very highly sheared environments. So if you watch the radar here, you'll see that we do have quite discrete elements along this confluence band. This is going to be our supercell of interest right here. But notice as it goes into the far northeast corner of Mississippi, it starts to cluster a little bit together. We almost get slight upscale growth here with some more updrafts on the southwestern flank of this dominant supercell. And I'm going to take a closer look here with our vortex-centered, or storm-centered radar loop. This is from Peter Corman on Twitter. Go ahead and follow him at the handle there. But if we play this, watch what happens here with these storms. So this is all the way down in central Louisiana. We start to see that updraft take over, but you see that we do get some semblance of clustering here as this cluster moves into northeast Louisiana. This is Interstate 20 right here. So we're moving into northeast Louisiana, close to the Mississippi River, and you see we get some clustering here. We have a lead supercell right in here. You can see that somewhat of a flying eagle look there. We also have updrafts on the backside. This is what's helping it to resist getting just torn apart by this strongly sheared environment. And as a result, you see eventually we get that supercell to take over, and we get a very strong tornado genesis right on the east side of the Mississippi River. So this is going to show its head a lot more when we approach the Amory, Mississippi tornado. We'll take a look at that in a second. But for now, know that the clustering and maybe slight upscale growth in these very highly sheared environments can allow these storms to survive a little bit longer. And you see a lot of these updrafts down here, these more discrete rain showers, they have a very difficult time sustaining. If we go back a little bit, you'll see they try to pop up along that confluence band, but a lot of them just get shredded because they aren't able to sustain in this very strongly sheared environment. With this northern storm here in far northeast Louisiana, we get a little bit of clustering, a little bit more updraft activity on the southwestern flank to basically shield it a little bit from the strong wind shear and allow it to survive a little bit longer in these environments. And if we look at our Jackson supercell over here as well in far southwest Mississippi, you can see the same thing. We get a lot of these updrafts to fire up, but you see some early clustering with these updrafts, particularly in this region right there. And as a result, continued storm merges as well. And as a result, you get a strong supercell out of that. Even though it does stay discrete, it's a little bit of difference between staying discrete and clustering initially. The Rolling Fork supercell was quite discrete up here, but we needed some updrafts to cluster it along it and close to it to help shield it from that strong shear, and that is how we maintain a discrete supercell that eventually became dominant and stayed discrete, producing a very strong tornado. Also, this environment was improving with time. We'll look at our sequence of rapid proximity soundings here in just a second, but this environment was improving with time. As we saw with our observed soundings, the moisture was increasing as we went into the late afternoon hours, as was wind shear, as that low-level jet started to jump right at and just after sunset. So this environment was also improving with time, really maximizing as this storm crossed the Mississippi River and began its path of destruction through Mississippi. Now, one thing to note here, we'll go back to our satellite view, and so keep an eye on our storm right in here, and you'll notice what happens right before we lose daylight here on the visible satellite. So we start this loop here, and you'll see that storm really shoots up with its overshooting top right before sunset, right just after 0Z, 7 p.m. Central Daylight Time. Very significant overshooting top there. You see the shadow from the setting sun, the sunlight coming this way, very strong shadow from a very strong overshooting top with that particular storm. And we'll also see on the infrared satellite that our storm really perks up as far as cold cloud tops. The colder the cloud tops, the taller that storm is, the more robust that updraft is. So you'll see right as it crosses into northeast Louisiana, we'll keep an eye on this particular storm right here. That is our Rolling Fork storm. And you'll see the cloud tops, those darker colors are colder cloud tops. You'll see it really spikes and those cloud tops really cool as it crosses the Mississippi. Strong overshooting top right in here. You see that little dot of darker red there. That is our overshooting top. Very cold cloud tops there as it crosses into Mississippi. And that occurred right as it moved into northeast Louisiana. Another impressive feature of this storm on radar was the vortex hole or weak echo hole that developed after it crossed the Mississippi River. So just to give you some context here is Lake Providence, Louisiana. Here is the Mississippi River right in here, and Rolling Fork is up in there. So you'll see on the radar data as we scroll through here, it starts to take on some low-level shear as it approaches the Lake Providence area just after 0Z. And it starts as it approaches the river to really get that yin and yang, so to speak, those greens and reds really flipping around, starting to get a rotational couplet as it crosses the river. And then after it crosses the river, it takes on a very interesting shape, really strong couplet there approaching south of Mayersville and Rolling Fork. And right here, you'll see a very, very well-defined vortex hole or weak echo hole here. We talked about this in previous case studies, such as the Greensburg, Kansas tornado from 2007. Often you'll see these vortex holes really well on mobile radar data, higher resolution data. But to see a vortex hole this stout, this well-defined, and this large on WSR 88D data is pretty impressive. As you can see, it's associated with a very strong couplet approaching Rolling Fork. It was very quickly a strong to violent tornado, and this vortex hole maintained itself for quite a while. You can see here the next few scans toward Rolling Fork. It does fill in a little bit, but as it goes over Rolling Fork, you can see that vortex hole still in place right there associated with that strong couplet, debris signature as well as it goes through town. So this is some very impressive radar data, especially from a WSR 88D. Obviously a very strong couplet, but that vortex hole, you don't see that often with these kinds of supercells from a WSR 88D. You see that a lot more on the high-resolution mobile radar data. Thankfully, we also have some of that with this particular event. As part of the Perils project, the C-band Doppler on wheels, or the COW-1, was scanning this particular storm. So we get some really good high-resolution data from much closer than the WSR 88D was here. So this is some very helpful data for us to look at. So this is the Dow data. You can see it starts to take on a very strong shear signature there approaching Lake Providence right as it crosses the river. And then you'll see here in just a few scans really starts to develop a very strong couplet, and that vortex hole wraps around. I mean, that is just super impressive. Very clear weak echo hole or vortex hole or weak echo eye, whatever you want to call it, and just a very large weak echo hole as well. Not often you see a weak echo hole this large, but associated with this strong of a couplet, this was a very large tornado very quickly, and therefore took on some very interesting radar characteristics. Again, that vortex hole maintains itself as it moves out to the northeast, a little bit farther out of radar range, but you can still see that some semblance of vortex hole there. So very interesting radar data. These vortex eyes or weak echo holes are often associated with the stronger tornadoes, especially ones vortex holes of this magnitude. So very interesting radar data associated with this storm. So the tornado continued through places like Silver City and Midnight, and then we eventually see a very brief disruption in the tornado production of this storm before a second tornado occurs near the town of Blackhawk, moved across I-55 near Winona. And then for quite a while after that, after the second tornado dissipated, we see a cease in the tornado production with this storm. Unsure why that's exactly the case. It does look like the overall storm mode, at least briefly, gets a little bit messier. You see a bunch of these showers riding up into the inflow region of the storm, perhaps some instance of destructive interference with these showers, but it would quickly take a turn and regain its discrete supercell characteristics. You can see some of the mergers there. Going into the forward flank could be some constructive interference at this point. It's hard to say for sure why the tornado production stopped for such a long time before regaining it. You can see it starts to take on that supercell shape once again. And this was, again, a case of where slight upscale growth, slight clustering of the storms probably helped this storm to regain its balance. If we zoom back out just a little bit and take a look at the radar picture going through, here is our Rolling Fork storm. So keep an eye on that region. So you'll see it continues on for quite a while as a semi-discrete supercell. Then we get a bunch of this shower activity to start streaming up into it, probably off another confluence band out here. You can see kind of a line of that convection there. Probably another confluence band initiating some showers that go up right into the forward flank region of that storm. So at least briefly, the semi-discrete nature of this storm was somewhat disrupted. But eventually, you see that we do have somewhat upscale growth. We have these updrafts, these thunderstorms back to the southwest, creating some semblance of a small line segment here with this leading Rolling Fork supercell on the very leading edge of that. And again, it's the same kind of concept. Perhaps this slight clustering or slight upscale growth of this little segment with this supercell on the leading edge may have helped it withstand that shear that may have been very tough to overcome as far as a single updraft. And then we were able to get a renewed period of tornado production after that, perhaps influenced by some of these cell mergers, but likely more influenced by the slight upscale growth to help resist getting torn apart by that shear and rebalancing itself to become a significant tornadic supercell as it neared Amory. We'll zoom back in here, go through the progression of this storm as it moved through Amory. You can see a very quick transition, very classic supercell structure here, and with that very strong reflectivity gradient on the forward flank, very strong hook echo appendage there on the leading edge of that line segment, very quick, rapid strengthening of the low-level rotation as it moved through Amory with a very significant debris ball. You can see the debris signature down here, very, very large debris signature in the correlation coefficient. So no doubt was a significant tornado. And as we said, this was an EF3 with winds over 150 miles an hour. So very strong tornado moving through Amory and near Smithville, Mississippi before it somewhat dissipated and eventually merged into a line segment, became a bow echo type feature, bookend vortex. You can see here with the progression as we zoom back out. The mode definitely takes a turn for the worse as far as tornado production goes, but we see a little bit of a bookend vortex develop as that supercell is swallowed by the overall line. And you see that tornado and rotation ongoing for quite a while in that somewhat of a comma head type feature on the northern end of that portion of the line segment. Would continue to produce tornadoes as it moved into Alabama. Northern Alabama, several tornado reports up in here as well. So a very potent supercell that did quite a lot of work here in this particular environment. Well, let's take a look at this environment and how it changed throughout the day into the evening on Friday. This is a series of RAP model soundings. We're going to take a look at two different locations. First, we'll take a look at Jackson, Mississippi, and then we're going to look at Starkville, Mississippi, up farther northeast, closer to the track of where the Amory tornado went. So first, we're going to start out with Jackson. We'll start out at 12Z and go through about 4Z several hours after sunset to see how the environment changed throughout the day. So we start out at 12Z. We already kind of looked at this fairly deep moist layer, but a bunch of dry air aloft. And again, that mixing was a concern going into the afternoon hours. But watch what happens. Keep an eye on that skew T throughout the morning and afternoon. We really deepen that moist layer, and this is going to be at 21Z, so 4 p.m. Central Daylight Time. That moist layer is all the way up at or just above 700 millibars, so a very deep moist layer. We have had some influence from the mixing, 82/62 there, slight inverted V profiles in the sounding, but once again, that was expected to be mitigated by strong low-level warm advection as we went into the early evening hours. Photographs by this point somewhat favorable for severe weather already, although not a great deal of curvature there in the low levels of that photograph. Still adequate for supercells and a fairly strong deep layer shear for supercells working its way in at this point. Watch what happens though as we go into the evening. Watch that photograph. That photograph jumps pretty significantly. This is at 0Z. By this point, that mixing had been gone. We had gone from 82 over 62 at 21Z, and in just a couple of hours, we had gone to 73 over 69. So the temperatures had cooled thanks to the sun going down, and that moisture had really, really ramped up thanks to that surface low deepening and that low-level cyclone really ramping up. And we can see that from the hodograph. Take a look at the hodograph as well. We'll go from 20, here's at 20Z, very minimal low-level curvature to that hodograph. Not super favorable for significant tornadoes. We go from a 1 kilometer wind of about 20 knots or so. And in just a matter of hours, that increases here at 0Z to right about 50 knots. So we jump up about 25 knots, and we continue to increase that low-level jet throughout the evening. This is at 2Z. So about 9 p.m., that low-level jet, that 1 kilometer wind, had increased even more to about 60 knots or so. So we'd gone from a low-level jet, a 1 kilometer wind of 25 knots at 20Z, to about 60 knots at about 0 to 2Z. That's a 35 knot increase in low-level jet. That is going to do wonders for your hodographs, and no wonder these significant tornado threat ramped up significantly right at and just after sunset, given these hodographs. Also, thermodynamics favorable for supercells as well. Low-level lapse rates a little bit on the weaker side, but again, when you have strong low-level shear, that can overcome weaker low-level thermodynamics. Overall, over 1,200 joules per kilogram of mixed layer CAPE, about 60 joules per kilogram of 0 to 3 kilometer CAPE. So low-level instability was not was definitely adequate for this particular event. But these shear profiles, man, just incredible. About 60 knots of deep layer shear favorable for supercells. Given a discrete supercell mode, this very strong low-level shear, almost 400 meters squared per second squared of effective storm relative velocity, very strong veering of those low-level winds with height, very strong curvature in the hodograph. No question this was a significant tornado environment. Let's take a little bit of a closer look at the hodograph as well. We do see, again, that very strong curvature in the low levels, and if we were to transpose our hodograph onto our supercell, and we've done this exercise before where we can use the wind profile in the hodograph to give us a rough estimate of what the supercell is going to look like, if we're going to see more of a high precipitation mode, low precipitation storm mode, etc. So let's take a look at that. If we were to look at our wind profile and transpose that on our supercell, mesocyclone region here, and that precipitation going to be vented somewhat away from that mesocyclone region there. And storm motion more going maybe somewhat toward that forward flank precipitation core, but overall not too bad. If we look at our data here, this is what our supercell looked like, and you can see a very similar profile on what we actually saw on radar to what our wind profile looked like on our hodograph. This was our mesocyclone region, obviously tornado ongoing at this point, approaching Rolling Fork, precipitation vented off away from the mesocyclone region, and so our wind profile did a pretty good job of showing us that we were going to see a fairly visible any tornadoes that this storm would produce would be fairly visible, given that we don't have a bunch of rain falling out ahead of this storm. And you can see a number of pictures here that the tornado was very, very visible. This is from my friend Aaron Rigsby, who was chasing this storm. Very, very visible tornado for quite a good chunk of its life cycle, especially in the early portions as it moved through Rolling Fork towards Silver City. Another facet of the hodograph we can look at is the storm relative inflow. That is basically the vector from our storm motion vector back to our hodograph from about 0 to 1 kilometers. And the larger that vector is, the larger your supercells are going to be. Generally, the rule of thumb is a 0 to 1 kilometer storm relative inflow vector of greater than 35 knots is a great recipe for larger supercells. And we see about 30 knots here or so. And we go 1, 2, 3 ticks or so. It's about 30 to 35 knots, right in that sweet spot for decent-sized supercells. These were not your typical warm sector little beans that you might see that may have struggled. We saw some of those smaller storms down to the south a little bit. Those struggled. Those tended to struggle, perhaps because storm relative inflow was a little bit weaker early on. And in this very highly sheared environment, those very small storms may have had a difficult time surviving because of the strong shear and the stuff we talked about earlier. But this particular supercell, the Rolling Fork storm, you can see fairly large size supercell, definitely not a bean, so to speak, definitely a decent sized supercell given strong storm relative inflow. We can also look at storm relative outflow in the mid and upper levels. Generally a rule of thumb, is a storm relative outflow greater than about 40 knots above 6 kilometers. A deep layer of that 40 knot plus storm relative outflow aloft generally helps to vacate that precipitation away from the mesocyclone region, making for much more viewable and visible tornadoes. So we look at our 6-kilometer vector. That's about the top here of that green portion of the hodograph. Generally above 40 knots or so, a deep layer of that vector from the storm motion vector to our hodograph above 6 kilometers. We want to see that a little bit greater to favor more low precipitation modes, and high precipitation modes tend to favor much weaker storm relative outflow aloft. Here we see about 20 to 30 knots or so, right above 6 to maybe 8 kilometers or so. That's a little on the low side, but somewhat close to that classic supercell spot, about 30 to 35 knots or so. That's why we did see, again, a more visible tornado with this particular supercell, at least early on in the life cycle, and that is due to the fairly decent storm relative outflow aloft. So the main takeaway here from this sequence of Jackson soundings is that the thermodynamics definitely became much more favorable closer to dark. We got rid of that mixing, and we heightened that moist layer quite a bit throughout the afternoon, and that wind shear profile became pretty favorable for strong to violent tornadoes in this kind of thermodynamic environment. So let's take a look now at the Starkville sounding from northeast Mississippi. It gives us an idea of what the supercell was experiencing closer to when it produced the Amory tornado. Very similar start here. This is at 12Z at Starkville. Decent moist layer up to about 850 millibars, but a fairly deep layer of dry air aloft atop that moist layer. That would continue throughout the day. We had a little bit more influence from that aloft, between about 500 and 700 millibars there at Starkville off to the northeast. So a little bit less favorable thermodynamics, perhaps farther to the northeast. And that would stick around a little bit until after dark. You can see here fairly well-mixed air, 80 over 61, even to 1Z. We hadn't really fully gotten that mixing, that well-mixed layer near the surface to erode or become mitigated from that strong low-level warm moist advection. That would continue. That would happen, though, over the next few hours, 78 over 64 by the next hour at 2Z. So our thermodynamics, definitely in the low levels, became much more favorable for tornadoes. And that little kink aloft we saw in the skew T, was mitigated as well. But you see the same thing happening there as well. The hodograph really jumps in magnitude, especially the low-level shear magnitude by 2Z here. Just a super favorable look for supercells, very similar to the Jackson sounding, with very strong low-level shear, over 400 meters squared per second squared of effective storm relative helicity, with a decent amount of streamwise vorticity there in the low levels. That was going to be a great recipe for significant tornadoes. And when you see the hodograph continue even more, a little bit of convective contamination there in this particular sounding, but the hodograph continued to become more and more favorable for long track, strong tornadoes there. As we went into the evening hours, this is at 4Z, thermodynamics very favorable at this point. Over 1,300 joules per kilogram of mixed layer CAPE, almost 100 joules per kilogram of 0 to 3 kilometer CAPE with a very favorable looking hodograph. So the environment definitely drastically improved as we went into the evening and nighttime hours, and hence we got to see multiple strong tornadoes from this supercell. And even if the thermodynamics were not quite as good, this strong low-level shear was going to be able to overcome that. We've talked again about that in cases previously. The Henryville, Indiana case from 2012, March of 2012. The storms down in Kentucky on that day were in a very hostile thermodynamic environment, but because the shear was so strong, especially the low-level and deep layer shear, those supercells were able to overcome that. When you have a mature supercell ongoing, moving into a more hostile environment, it's going to last even though the environment becomes more hostile, because it's such a steady state storm, especially in these kinds of environments. So that's going to do it for the bulk of the meteorological analysis. I want to just point out quickly the horizontal vortex that was associated with this tornado. Here's a shot from Aaron Rigsby. Once again, you see that horizontal vortex there with the wedge tornado, the main wedge tornado ongoing. This is a shot from my friend Max Olson as well. Very well-defined horizontal vortex there, and we have talked about this before, that these horizontal vortices are associated with usually strong to violent tornadoes. We've seen it many times before. The Henryville, Indiana tornado from 2012, Tuscaloosa from April 27, 2011. Here's a video shot of that. Well-defined horizontal vortex there throughout a decent portion of its life cycle. So these horizontal vortices are usually reserved for the strongest of tornadoes, and this one definitely fit the bill. Such a menacing shot there from both these guys. Really awesome look at this tornado with the horizontal vortex. There's one last thing I want to talk about before wrapping this video up. As some of you may know, there were a few storm chasers that were directly impacted by the tornado in the town of Rolling Fork. And this is not meant to bash or badmouth anybody. If you've been chasing for any length of time, you've put yourself in a precarious situation, you've made mistakes. It happens to everybody, myself included. But this instead is going to be hopefully an educational take or educational discussion about some things we can do to prevent these kinds of mistakes in the future. I still have some questions about how anybody was in a precarious situation with this particular tornado. Obviously, it's at night. Yes. Obviously, the storm is moving very fast. Yes. But one of the storm chasers impacted said in their video, "Where is this thing?" You probably should know that before you start to get close to the path or in the path of an oncoming tornado, especially at night. So just looking at this storm in general, this was a fairly easy tornado to chase. Obviously, any tornado is going to be difficult to chase. It's going to have its challenges, but this one was fairly easy to chase. Obviously, we said it was moving at 60 miles an hour and was at night, but overall, as we said, this was a very visible tornado. As we see from some images here, this tornado was not very rain-wrapped for quite a bit of its life cycle, so it was quite visible. There was lots of lighting to illuminate it. This was in the Mississippi River Delta, so it was not 100 miles east in the trees where it was a lot more difficult to chase. This was in the Delta. The terrain is flat. There's not a lot of trees. The roads are good. And this storm did not take on any deviant motion. This tornado was not deviant at all. We've talked about deviant tornado motion in the past for cases like El Reno, 2013, etc. But this storm did not exhibit any deviant tornado motion at all, and we can use our deviant tornado motion technique from Cameron Nixon. I'll put a link to his article about the technique we can use to forecast deviant tornado motion in the description below. But if we look at our Jackson sounding here, we're going to use the 2Z Jackson wrap proximity sounding here. We're going to do our deviant motion technique. So we plot our storm motion. For this exercise, we're just going to use our plotted bunkers right mover storm motion. Next, we look for the mean wind in the lowest 500 meters of the atmosphere. It's a little tough to tell. It looks like it's somewhere right in here, so that's our 500 meter wind. The average of that going to be somewhere in here, I would say. And then we take the midpoint of these 2 points. That'd be somewhere in there. And we draw our vector, and that is our deviant tornado motion vector. Well, you can see, here's our storm motion vector, drawn in blue here. And here in pink is our deviant tornado motion vector. Not a lot of difference between those two. So these tornadoes were not expected to be deviant at all. And this is in part the case because faster storm motions, the storm is moving at about 50 to 60 miles per hour or so, faster storm motions decrease the likelihood for deviant tornado motion. And you can see by the path that they were not deviant in the slightest, really. If we look at our damage assessment toolkit here, this is the tornado path of the Rolling Fork tornado. You can see it is pretty much a dead straight line. Of course, it has its very slight wobbles here and there, but nothing like, say, in El Reno, where it has extremely deviant motion and can catch chasers off guard. This track was a very straight line track. So there really was no excuse, in my opinion, of being in these particular situations. Now, again, I'm not trying to bash anyone, but I want to just say that if you plan on chasing tornadoes and you like to get up close, doing this deviant tornado motion technique is really, I think, a critical portion of it should be a critical portion of your forecasting for a particular chase. Because if you have a situation where there is going to be a lot of deviant motion, that might be a situation where you probably should stay a little bit farther back from these tornadoes instead of being caught off guard in those types of situations. Again, this was not a situation where deviant tornado motion was a thing. And so they really shouldn't have been able, among all those factors we talked about, very visible tornado, very good terrain, good roads, should not really have been caught off guard by this tornado. And again, chasing in the southeast is a different animal. It's not like the plains where the storms may move at 30 miles an hour and you can see the tornado coming. It's very visible all the time. This is the southeast. It's a different animal. When you have upper echelon profiles like this, especially strong shear profiles like this, you really have to be careful about what you're doing. And I think using things like the deviant tornado motion technique, like we discussed as part of your forecasting, and really trying not to lose situational awareness. Again, we've all done this before. We've all lost situational awareness before at times, but after those mistakes, you learn from them. And I hope these guys will learn from what happened, and hopefully, I know there's a lot of new chasers watching the channel here, and newer aspiring chasers that watch the live streams of chasers like this, and the channel and our channel here. So I just want to put that out there, and don't want those of you who are new or aspiring chasers to look at this and say, wow, that's pretty cool, that's how chasing should be done. It really shouldn't. I'm not here to police anybody's chasing. I don't care how you storm chase, as long as it doesn't put anybody else in danger. I have no say in how you should storm chase, but we really need to be careful and set a good example for chasers, new and aspiring chasers, to avoid these kinds of things. And by using the deviant tornado motion technique that we discussed, keeping situational awareness, and keeping your head on a swivel at all times, staying back a little bit farther if the environment is so upper echelon, like a case like Rolling Fork. Those are things that you can do to eliminate these kinds of mistakes in the future. So that's going to wrap things up for this breakdown of the Rolling Fork tornadic supercell. Obviously, probably the tornado of the year so far. Strongest tornado for sure that we've seen this year, and hopefully that remains the case, although the upcoming period looks to be very, very active as we head into April. Hopefully we don't have any repeats of what we saw back on Friday, March 24th. So that's going to do it. Thanks for watching, and we'll see you in the next video.